Hello, this is Mr. Huff, and I want to talk to you about inferential statistics. Look at the first word here, inferential. Do you see the word inference or inferring? That's the key word there. When we're talking about inferential statistics, we need to think about times where we don't have information for an entire population. So this brings us to comparing a population versus a sample. A population, you're getting measurements from all members. If you're looking at parts, you measure them all. If you're measuring the student height, you measure all of the students, okay? And if you're talking about a sample, you're measuring a set of those or a part of the population, not all of them. What inferential statistics lets us do is we can estimate and we can forecast an outcome based on an incomplete set of information. So we don't have to measure everything. We can take a few measurements and have an idea about what's going on. And that is very powerful. There are often places and times where we can't measure every single thing because it would just take forever to do, but we can take a set of those and assess the quality using statistics. So this is where sample statistics comes in. That's inferential statistics. Let's pull all of this up. So in population standard deviation, we are looking at the spread of data within a population. So we're talking about all of them. And in order to do this, every member has to be measured. In sample standard deviation, you have an estimate of the spread of data within the population. You do not have a data value for every member, and we are using a subset or a sample of the data to generalize the results of or to the larger population. So this lets us just say, hey, if I measure 30 of these, I know what's happening with all 300. These are the two formulas. So we've talked about sigma over here. This is the standard deviation of a population, and this is the sample standard deviation. Go ahead and take a moment to jot down this formula. S is equal to the square root of the sum of the measurement minus the sample mean squared divided by the number of the sample minus 1. Okay, so some differences are in population, we're using the Greek letter sigma. In a sample, we're using a lowercase s. The individual data values are the same, but if you look at population, we're using mu for mean, and in this case, we're using x bar or bar x for the sample mean. So this tells us that it's not the complete population. Over here, if we are talking about the size of the population, we're using a capital N. If it's a sample, we're using a lowercase n to help us remember we didn't measure every one of these. So this is the population for where everybody is measured, and this is the sample standard deviation where we measure a subset. Let's talk about the difference here, the n versus n minus 1. So the n is the number in the entire population. N minus 1 includes a subtraction. So we have n, which is the number of our sample, and we're subtracting one value. And what that lets us do is we decrease the size of the denominator here, and that increases the size of the sample standard deviation. And this accounts for uncertainty. Because we didn't measure everything, we have to inflate that sample standard deviation to accommodate for the uncertainty because we did not measure everyone. All right, and it's really, really similar to what we did before. Let's just go through this example. So in this case, first thing we have to do is we have to calculate the sample mean. And if you look at this, we're still adding up all of the values and we're dividing them by the number that we measured, not the number that we have, but the number that we measured. And we're using X bar to represent the mean of the sample. So add up all the measurements you take divided by the number that you measured. So it's essentially the same as the population mean. Okay? But in this case, we're looking at sample standard deviation. We've looked at this set before. So here's our data set. So what we have to do is add all of those together and divide by the number that we have. 524 divided by 11. We get an average of 47.63. And then for each data value, we have to take the measurement minus the sample mean, and then we're going to square that number. So let's look at the math for that. So we take the number 2, and we subtract from the mean, or subtract the mean from it, and then we square that value, and we get 2082. Looks real similar to what we did before. And you do this for every measurement. So you got a 5, then a 48, and 49, 55, and so on and so forth until you complete all 11 of those. Okay, so we've calculated all 11. And then we add all of those together. We get 5,024. And then this is where the difference is. We divide by the number of sample values minus 1. This is to account for uncertainty. Normally it would be 11. We have 11 here, so we take 11 minus 1, and that gives us 10. So we end up with 502 for our sum of the squares. And then we calculate the square root of that result, and we get 22.4. If you remember from our previous discussion, this same number, this same data set gave us a population standard deviation of 21.4, and now we are looking at 22.4. So your sample standard deviation is generally going to be higher than your population standard deviation because of the uncertainty we add in. And then it talks about rounding and stats. I don't care so much about rounding. Give me 4 important numbers. Okay, and then this is the same slide we saw earlier, but they add this little thing at the bottom. And we need to turn this into a sentence. This is a really important idea. It's worth writing down. As the size of your sample increases and approaches the number of members in the population. So this year at Heritage High School, we have around 1,100 students. So if we started with 10 students, that would tell us a little bit about 1,100 students. But if we had 800 students, that would tell us a lot more compared to the population. And if we had 1,000 students versus the 1,100, we know really accurately pretty well what's happening with our standard deviation. So as the number of samples that you take approaches the number of in the population, your sample mean, or your sample standard deviation, your sample standard deviation approaches sigma, which is your population standard deviation. So the more samples you take, the closer you get to the population sample standard deviation. They become similar. Let me try that again. So as the number of samples approaches the number of members in the population, the sample standard deviation approaches the deviation of the population. And then they have a couple of examples. So if you're using, when you would use this, when you would use the population standard deviation, this is if you have measurements for every member. So let's say, and it talks about HCT scores. What if we measured the height? We wanted to know the average height of students at Heritage High School. We would have all 1,100. We would go measure the height of each one of those, and then we could use population standard deviation. But if we wanted to use a sample, instead of measuring every student, we would measure every student in the commons area during bead tassel, and that would be a set of the students. So it's not all 1,100. It would be like a couple of hundred of them, and then we would know a standard deviation based on a sample that would probably be really close to the actual standard deviation of the population, but it's an estimate, it's a forecast. And this is the place where I need to stop.